Hello, welcome back to this course on discrete mathematics, and today we are going to continue the same topics of logics of compound statement part 3. Today we are going to examine few more points on some of the logics, and we are going to see some of the properties that are very important for our logical conclusions. Let's dive into the first part, which is about the tautology and contradiction. So what is a tautology? A tautology is a statement that is always true. No matter what you do, the statement always remains true. It's something like sun always rise in the east. You can't change that. Likewise, you can think of a logic in which it always remains true. For example, as you can see here, P or negation of P will always be true. So that's a part of negation law. And there is another thing is called contradiction. By definition, a contradiction is a statement that is always false. No matter what it is, it always remains false. And you can also express the same thing by means of a logic. So here is an example of it, where we say P and negation of P is always false. That's again a part of the negation law. So here is this truth table where we are given with the value for P and value for P or negation of P. P and negation of P is given. So whenever you see the value of P to be true or false, the tautology, which always remains to be true. So this part is the tautology and this part is the contradiction. Let's see more on this logical equivalence. The logical equivalence means that two sides always have the same true value. So when both sides has the same true value, we say they are logically equivalent. So we use the symbol like similar to, or this symbol that shows both directions. But one thing, don't get confused with that of a biconditional. Biconditional is not same as logical equivalence. So for logical equivalence, you can also think about conditional and contrapositive. Inverse and converse, they are logically equivalent. Here is more information on logical equivalence of and. P and tautology is similar to P because the tautology is always true value, and what you have to consider is if P is true, then automatically the output is going to be true. So you don't have to worry about the T, which is always true, just worry about the value of P. So that's the identity law. So here is the truth table. T is always true no matter what it is, because that's the tautology, and you have to, the value or the output of this depends on P. Whenever P is true, the output is true. Here is another one, is called domination law. So here is P and F. F is like a contradiction or false value. So you have whatever the value of P, the output is going to be false, because here F is going to dominate your output. Yes, F, which is always remains false no matter what is P, whether it's true or false, the output is going to be false. So that's the domination law. Then we have few more laws. The first one is called idempotent law. So P and P is equal to or similar to P, because if P is false, the output is false. If P is true, the output is true. Yeah. So the output follows the value of P. In the same fashion here, for cumulative law, P and Q is similar to Q and P. So you can think of this logical expression, and here is the truth table where you are given with both P and Q values. So you can see that the output part where P and Q section as well as Q and P section, they are same. They are logically equivalent. Here comes the other one, is called the associative law. P and Q and R is similar to P and Q and R. So that's interesting, because you have to express this whole expression by means of truth table to prove it. We have P, Q, R, 3 inputs. So you have all possible inputs given, like you have 8 inputs given to the system, and you can try to find what is P and Q, or P and Q and, or in fact it is P and Q and R. So we have this part over here and this part over here. So P and Q and R, and P and Q and R. So you can see again they are equivalent. So we can prove that this property of associative law with regards to AND operation, they are equivalent. Then comes the identity law for OR. As with AND, we saw that P and T, in that case, because T always is true, so P follows T. Just to recap that, I'll just go back and show you this part where we talk about the tautology. Here it is. Here it is. So P and T, where in fact the output follows the value of P, because we know that T is always true, so the output depends on the value of P. If P is true, the output is true. If P is false, the output is false. So I just want to get clear with this idea of logical equivalence of AND for the identity law and the logical equivalence of OR for identity law. They are quite different. So for AND, P and the true value, so the output always follows P. But for OR, P or T, the output always follows T. And P or F, that is the always remains F, which is the domination law, the output always follows P. P or P, again it's P. P or Q is equal to Q or P, cumulative law. And associative law, P or Q or R is similar to P or Q or R. So why don't you try these using truth table and try to prove it, just like the way we did for AND. We already showed you an example using truth table to prove all these laws for logical equivalence of AND. Now I have all these logical equivalence expressions for OR, like identity law, domination law, idempotent law, cumulative law, associative law. Why don't you try it out? Try to use the truth table and prove it just for your satisfaction. Okay, let's see some of these corollaries of associative law. So here is the expression given to us: P and Q and R is equals or equivalent to P and Q and R. Then comes this OR, associative law based on OR. P or Q or OR is similar to P or Q or OR. So that's very similar to like 3 plus 4 plus 5 equal to 3 plus 4 plus 5. Right. So only works if all operands are same. So if all operands are same, then it's fine. So we have to see whether when we have these combinations of different operands, will it work or not. So let's look at some logical equivalence of NOT. Here it is, the double negation law. Negation of negation P is similar to P. We know that the negation part cancel out, so you have the P as the result. P or negation of P is equals to or equivalent to the true value. We have already seen that as the tautology, and that's the negation law as well. No matter what the value of P, because if P is 0, the negation of P is going to be 1. So when you OR this two value, you are getting a true value. P and negation of P is equivalent to false. Yes, that's again a negation law. In other words, it's kind of a contradiction, because when you have 0 as P value, P is 0, and negation of P becomes 1. So when you AND these two values, the output is going to be false. No matter what the value of P is, if P is 1, again 1 and negation of P becomes 0. So when you AND this two value, it becomes false. Now we are coming into this hot topic of DeMorgan's law. Yes, DeMorgan's laws are very important, and these laws can help us to solve many logical equations. Yes, I hope you can get familiar with this more important DeMorgan's law. It's quite important for us to follow all the laws related to this. Yeah, as I told you, probably the most important logical equivalence that you have here. Okay, this is another important expressions that you can get familiar with. We will come across later many times. That is to negate P and Q, or if you want to negate P or Q, you flip the sign and negate both P and Q. What does it mean? It means that if you want to negate P or Q, I mean here in this example we have P and Q, so you are putting a negation in front of P and Q. So that is equal to, now you are going to flip the sign. You are flipping the AND into OR, and you are going to negate both P and Q. That's what you are doing, right? Here you are actually flipping from AND to OR, then you are changing the sign of P and Q, or in other words you are negating both P and Q. That's the same way you do for OR as well. If you want to do for OR, negation of P or Q is similar to negation of P and negation of Q. Yeah, these two important logical equivalence, we are going to use it in many other places later on for solving some logical expressions. So try to understand. If you want, you can also try to prove it using truth table and try to understand this concept. So here is an example where you can see how this whole thing has been expressed by means of truth table. So you have both the P and Q as the input, and negation of P and Q you can found, it can be find. You can find it by means of P and Q. Then you have P and Q, negation of P and Q is given. Negation of P and Q is given. So now you can think about what is its equivalent there. There it is. So negation of P and Q is equivalent to negation of P or negation of Q. So this is one of the important observation. Then comes P or Q. For P or Q, if you want to negate P or Q, what you are going to do is, as you negate P or Q here, that's equivalent to negation of P and negation of Q. Yes, they are equal. You can see that these two are equal, and again you can see here that these two are equal. Well, let's move on and see more equivalence operators. In comes here with the distributive law. P or Q and R is similar to P or Q and P or R. Then you have P and Q or R is similar to P and Q or P and R. So this is the distributive law. Then you have the observation law, that's P and, in fact, P or P and Q is similar to P. Yeah, just imagine here, if P is true, then you don't really mind what is P and Q. In other words, you don't really want to know what is Q value. Once you know the P, that's going to be the, if P is going to be 0 or false, the output is going to be false. If P is going to be true, the output is going to be true. In the same way here, P and P or Q, the same thing happens here again. If P is true, the output is going to be true. You don't have to worry about Q. So how to prove two propositions are equivalent? So there are two methods to prove it. One is using truth table, but it's not good for very long formulas. It's too complicated and often we might come across certain mistakes. It's not easy to follow all the things in the table. or you can use the logical equivalence. Yeah, that's what I said. Some of the laws are very important, and these laws can be used for solving some of the logical expressions. Yeah, that's one of the preferred method. So here, as we go on, I will show you some examples on how we can prove using truth table as well as using logical equivalence. So let's start with an expression here. P implies R or Q implies R is equivalence to P and Q implies R. So this is the given expression. Let's do it by means of truth table. So P, Q, R, the three inputs are taken. Then you have P implies R, Q implies R in the truth table. Also you have P implies R, or Q implies R, that's also there. Then on the right hand side, P and Q as well as P and Q implies R is there. So you are trying to plot everything and trying to see whether they are equal. Well, after writing down all these things, you found that yes, they are equivalent. You can see that these two are equivalent. Fine. Now let's see whether we can do the same thing using logical equivalence. So here's the original statement. Now let's try to use some of the laws and try to prove it. Okay, initially we are going to use this implication definition, where you have P implies Q is similar to negation of P or Q. So that one you could use here. So on all three terms we are using it, the definition of implication. Then here again, negation of P and Q is similar to negation of P or negation of Q. We can use the DeMorgan's law. So you are using the DeMorgan's law. Then here negation of P or Q, in fact negation of P or R, or negation of Q or R. So using associative law, this is equivalent to negation P or R or negation Q or R. So let's do that part here. Now we are coming closer. So you can try to rearrange. You have many R's there, right? Yes, negation of P or negation of Q or R is there. So you can see that when you use idempotent law, when you say R or R, that is similar to R. So you can just write it as R, and that's it. There you are. Your left hand side is equal to right hand side. So in fact we have proved it. So there are two ways to prove the equivalence of two equations of a given expressions. Either you can go for the truth table or you can use the logical equivalence to express it. Let's have some parts using logical thinking. Okay, at a trial here, Bill says Sue is guilty and Fred is innocent. Whereas Sue says if Bill is guilty, then so is Fred. But Fred says I am innocent, but at least one of the other is guilty. So let's say B equals Bill is innocent, F is Fred is innocent, S is Sue is innocent. And our statements are like their statements are, Bill says that Sue is guilty, so negation of S, and Fred is innocent, so and F. Sue says if Bill is guilty, then so is Fred. So negation of B implies negation of F. So Fred says I am innocent, but at least one of the other is guilty. So F, that is if Fred is innocent, and negation of B or negation of S. So this is given to us. Based on this given part, can all the statement be true? So if you look back at the statement, you can check, can all be true? So let's try to show what is happening. So if it's all, or we are just adding up all the statement, you are having an AND value, as you can see. The three statements given by those three are here, and you have an AND operation between them. So you are trying to formulate the truth table. So as you formulate this truth table, you can see, you can write down the whole structure here. So for all the values that are here, you can conclude that there is some section that is not essential. For example, as we can think about the Bill, Fred and Sue. So BFS represents the Bill, Fred and Sue. Negation of B, negation of F, negation of S. So BFS, in fact BFS is representing the Bill is innocent, Fred is innocent and Sue is innocent. Negation of that means that they are guilty, right? Yeah, negation of B, negation of F and negation of S represent they are guilty. And now you have the three statements, the negation of S and F, negation of B implies negation of F, and finally you have F and negation of B or negation of S. So which means that the middle section is not really needed, only we need this three part, only this three part is needed. And among this three part, we are trying to see under what condition all are true. You can see all these values, only this part, those three are true. And there now we are going to examine, this is the section in which all remains true. So from this you can make a certain conclusion, though it's not clearly evident, you can make a certain conclusion that the true values are given to us. So all of these statements are true. We show that S, B and F such that the equation is true. So we have the original statement. Now let's try to form a similar output using the logical equivalence. We have seen what happened in the truth table part. So according to the truth table part, we come to know that Bill is innocent, that is true. Fred is innocent, that is true. But Sue is innocent, that seems to be false. And moreover, using the logical equivalence, let's try to formulate. So we are using the implication operator first, the law of implication, associative for AND we are using. We are trying to rearrange things. Then again using idempotent, we are eliminating F there. Then you are rearranging. Now you are observing so that you have S there. Rearrange it. Then you are having a distributive law there. Again you are using the negation law. Then comes the domination law. Therefore this we are using the associative law there. So accordingly what you have in the end is this part. Fred and Bill and the negation of yes. Yes, similar to the one what you got in the truth table, where you had the negation of yes. So this is just to prove that anything can be solved using truth table as well as the logical equivalence, but in fact logical equivalence method is more preferred as mentioned earlier. So what if weren't possible to assign such values as S, B and F? There are cases in which we don't able to assign certain values. So we try to use these logical equivalents to solve in the previous slides. So we come up with this rearranging part, and finally we come up with statements that can give us some output, but at times it cannot be done as we wished, because what if we weren't possible to assign such values? If we were not possible to assign certain values, now finally we are at a contradiction. See here, F equals T, that's the contradiction that we are arriving at. Yeah. Functional completeness. So all the extended operators have equivalence using only 3 basic operators, and or not, as we have seen, and there are many extended operators like NAND, NOR, XOR, conditional and biconditional. So anyway, we are always going to focus more on the basic operators. So I just want you to think about this. Can you write an equivalence of the 3 basic operators, or can you still try to perform some equivalence using other operators? Yeah, if so, that the group of operators is functionally complete, if you can do that. I just give you an example of this functional completeness. So let's think about this functional completeness of NAND operator. Show that NAND operator, a symbol is just the straight line, is functionally complete, equivalence of not. So here it is, P NAND P is similar to negation of P. This is the property there. And negation of P and P is similar to negation of P. Again the equivalence of NAND is popping up. Negation of P is similar to negation of P, the idempotent law. So equivalence of AND. So here what we have seen is equivalence using not. Now you can see equivalence using AND. So P and Q is similar to negation of P NAND Q. P NAND Q. So the thing is P NAND Q NAND P NAND Q. So that's of negation of P NAND Q. So equivalence for OR, because not and or the 3 basic operators, you can try to express the extended operators using these 3 operators. That's what we are doing. So once you do that, which means that things can be functionally complete. P or Q is similar to negation of P and negation of Q, that is DeMorgan's equivalence of OR operator. So as we do this and OR with NAND, we can thus do OR with NAND. Yeah, that can be done. Thus we can say that NAND is functionally complete. Yes, you can do the same thing for NOR. You can do the same thing, or try to do the same thing for other operators. It would be a challenge, but this challenge is quite worthwhile. Want to try to find it out. So today we have seen in this class various parts of operators and how they can be performed, and especially we have seen how we can solve a logical expression using truth table as well as using logical equivalence. And again we have seen some of the important laws, including the DeMorgan's law as well as the laws of tautology, contradiction, and associative law, distributive law, idempotent law, negation law. Just keep in mind these are very basic laws that governs the Boolean logic. So I like to stop here for this class, and still we are going to continue with one more lecture on this topic before we shift on to the next topic. So I am looking forward to see you in the next lecture. Until then, goodbye.